हेलो।
नहीं समझ नहीं आ रहा था क्या? लाइव में समझ नहीं आ रहा है कि
नहीं चेक कर लेंगे। आ रहा है साउंड आ रहा है।
वॉल्यूम मूव कर दो। वॉल्यूम मूव कर दो। आप अपने मोबाइल में सर भी चेक कर लीजिए साउंड। आपके में देखिए एरो आपको ऊपर का ऊपर नीचे पूरा नहीं है।
साउंड नहीं आ रहा है। हो गया होगा। इसमें क्या नहीं है? ओके सर।
Hello. Yeah. So, very good morning to all the participants. First of all, I would like to thank Bansal Institute of Science and Technology for inviting me for this FDP event. So, my talk is on passive voltage amplification in FED heterostructure. So, as the name indicates, passive voltage amplification in FED heterostructure. Till now, we have been discussing the devices.
आ जाएगा ना? कोई प्रॉब्लम नहीं दिखाई सेट करते हैं। हाँ बोलिए आप।
Hello.
हाँ नहीं क्लियर है।
Clear.
ऑडियो।
So, till now, we have been discussing like the devices which provide the amplification are known as active devices. So, here I am telling something new, passive voltage amplification in FED heterostructure. So, I am trying to get voltage amplification using passive devices. So, I think yesterday Deep Prakash sir had one session and he has shared some insights into negative capacitance. So, that will help me a lot. And I would thank Dr. Aslam for keeping Samazdar sir's lecture ahead of me. So, now the things will be a bit easier for me. So, let us proceed with this. Yeah, so this would be the contents of my presentation. First, I'll be going through motivation. Then we'll see about technology scaling, sub-threshold swing, what is an ideal switch. Then I'll move on to ferroelectric capacitor. Then I'll discuss on FED heterostructure through which we are going to achieve the passive voltage amplification. Then conclusion, future scope and the references. Yeah. So, as we see, this is the graph between normalized power and the gate length. So, as per the Moore's law, Gordon Moore, what he was saying in long back, he has said that the transistor size will be getting reduced as the day progresses. So, this is the graph with respect to gate length, and this is the normalized power. So, as we are miniaturizing the gate length, what is happening? The static power has started dominating over the dynamic power. So, we need a mechanism to mitigate, or not mitigate actually, but to reduce the static power dissipation. So, our research objective is to reduce the static power dissipation as well as dynamic power dissipation. So, what can be done? As we all know, dynamic power dissipation is directly proportional to VDD, the supply. Actually, the square of the supply. So, if we try to reduce VDD, there is a possibility of reduction in dynamic power dissipation. So, as we can see, this P dynamic is directly proportional to VDD square. So, if you try to reduce the VDD, the dynamic power will reduce drastically. But What happens if you reduce the VDD? The on current decreases and the speed of transistor also gets reduced. Now, in order to maintain the sufficient speed, the on current is proportional to VDD minus VT to the power alpha, where alpha is in the range of 1 and 2. So, now in order to maintain this on current, this threshold voltage has to be lowered. Now what happens? Now lowering threshold voltage leads to increase in off current. Off current is proportional to 10 to the power minus VTH by S. Hence, there is an increment in static power dissipation. Now this is a contradictory requirement. We started with decrease in dynamic power dissipation. Now in turn what is happening? The static power is getting increased. Now this is what I am saying. The contradictory requirement suggests a trade-off between performance and power dissipation always exists. There will be a trade-off between power dissipation and the performance of the device. Now one way to mitigate this problem is lower the subthreshold swing of the device. So this is what I have written. Reduction in SS allows scaling of VDD and VT simultaneously without any compromise with performance and power dissipation. Now the thing is how we can reduce the subthreshold swing of the device. Yeah. So subthreshold swing is a factor of two parameters. One is body factor and other is transport factor. So if you go by the expression, subthreshold swing can be written as 2.3 kT by Q 1 plus C depletion by C oxide, where 2.3 kT by Q is your transport factor and 1 plus C depletion by C oxide is a body factor. So there are two ways of altering the subthreshold swing. So now if we go by conventional MOSFET, in conventional MOSFET, the subthreshold swing is limited to 60 millivolt per decade. This is why, because just now I told you it is 2.3 kT by Q 1 plus C depletion by C ox. Now if you put the value of K, which is Boltzmann constant, T absolute temperature, and Q, which is the charge, it will come around 59.9 something. So it's approximately equals to 60. 60 into 1 plus C depletion by C ox. Now 60 into 1 plus something is obviously more than 60. So whatever may be the situation, we cannot alter the subthreshold swing in a conventional MOSFET below 60 millivolt per decade. Even if the oxide capacitance is infinite also, then subthreshold swing will be minimum you can get is 60 millivolt per decade. We cannot go below that. So this is what is written. For a conventional MOSFET, minimum value of SS at room temperature is 60 millivolt per decade if Cox is infinity. So this inability to reduce subthreshold swing below 60 millivolt per decade is an enduring challenge among the researchers. So as I told, it is a combination of two factors, body factor and the transport factor. So either we can reduce it by varying body factor or transport factor. So let's see. Before that, we'll quickly look what is an ideal switch. So as this is the characteristic for an ideal switch. This is the gate voltage and this is the logarithmic of current. So switch, normal switch has two states, off state and on state. In on state, the current should be as high as possible, and in off state the current should be ideally zero. So it has two possible states, on as high as possible, off as low as possible. If I go by the ideal value, on current ideally should be infinite and off current ideally should be zero. And there should be a abrupt switching. So within a small fraction of gate voltage, your switch should turn on. This is what is written, abrupt switching, and it should be very fast. So an ideal nanoelectric switch has zero standby power. as we all know, there is nothing ideal in the world. Everything is real. So this blue curve tells me about the ideal characteristic, and this red one tells me about MOSFET, conventional MOSFET, which we have been using, and the green one tells me about small swing switch. So as you can see, in this MOSFET, this off current is a bit higher, and in the small swing switch, the off current is less. So small swing switch can help us to mitigate this problem of performance and power dissipation trade-off. So there is a material which is known as ferroelectric material, which exhibits a property of negative capacitance, and that can help us to overcome the Boltzmann tyranny, which I told just previously, that in MOSFETs subthreshold slope cannot be scaled below 60 millivolt per decade. I told you it's a combination of two factors, transport factor and body factor. So in transport factor, like I don't know whether Shiven sir has given a few lectures. He has told you about TFETs and all, tunnel field effect transistors. So in TFETs, IMOS, there is a change in transport factor. But in ferroelectric FET, NC FET or NCPT FET or suspended gate FETs, in these all kind of FETs, there is a alteration in body factor. So my focus mainly will be on alteration of body factor to get subthreshold swing below 60 millivolt per decade. So as I told you, I'll be using this oxide, which is known as ferroelectric oxide, which possesses the property of negative capacitance, and it can help us to overcome the Boltzmann tyranny and reduce the SS below 60 millivolt per decade. Now, I have one material with me which is known as lead zirconium titanate. It's a well-known ferroelectric material which is mainly known for its ferroelectric properties and the negative capacitance. So the corrosive field for this particular material is 260 kilovolt per centimeter. Remnant polarization is 30.2 microcoulomb per centimeter square. And thickness of the material I have varied from 0 to 120. And there are few constants. There are few constants, alpha, beta, and gamma. Gamma, for simplicity, I have taken 0. This alpha and beta you can extract with these values. So VC equals to EC into TFE. TFE I am varying from 0 to 120. EC value I already know, to 60 kilovolt per centimeter. And similarly you can get the value of Q naught. PR you already have, and A. A is the area of heterostructure which I am taking. So A is actually 45 micrometer into 45 nanometer into 1 micrometer. And because it is a heterostructure, top layer is a ferroelectric layer and the bottom layer is a dielectric layer. Dielectric I have taken as a silicon dioxide, SiO2, whose dielectric constant is 4. And thickness I have taken as 1 nanometers. Now this is how my structure looks like. So this is my ferroelectric. Below to that I have a dielectric, and these are the two metals. Now if I go to equivalent of this particular heterostructure, as we know that a practical capacitor is a capacitor in which we have a resistance parallel to it. Now, but this structure is still called as non-leaky FEDE heterostructure. Why this is called as non-leaky FEDE heterostructure is, if I have some potential over here, if I apply some potential over here, so potential at point A, the potential at point A is unaffected by the presence of resistance and solely dependent upon the capacitance value. If some potential is applied over here, the potential, if I need to find at A, it will be solely dependent upon the value of capacitor. and resistance will not have any role. That's why this particular heterostructure is called as non-leaky FEDE heterostructure. And we are going to analyze this FEDE heterostructure. So this is my ferroelectric capacitor. So I have taken a isolated ferroelectric capacitor and I have applied a voltage Vs. Now the most common doubt what everyone has in negative capacitance is, can we get a physical negative capacitance? No, it's not possible. Like in case of negative resistance, what we study in tunnel diodes and all, it's a property of a device. Similarly, this negative capacitance is a property of a material. Means we cannot get that negative capacitance in the market this much value. So it's a phenomena, and it is a phenomena which is basically because of material. So there was one experiment which was conducted in UC Berkeley. They fabricated a capacitor with ferroelectric material, the same material, lead zirconium titanate, and they kept that particular capacitor, fabricated capacitor, and they put the probe in impedance analyzer. So it gave the value as positive. It gave the value as positive. Now the basic doubt which arises is, you are saying that it is giving a negative capacitance, but when you are analyzing the probe, putting the probe, it is giving the value as positive. Now one can question, if impedance analyzer is giving a positive value, how can you say that it is having a negative capacitance? The basic doubt what usually everyone has. So there are two ways actually. First of all, why it is not showing any negative value? First we go on to that. Then we'll think on how you can analyze, how you can say it is having a positive, how you can confirm the presence of negative capacitance. So why it is not showing negative value in the impedance analyzer? This thing is, negative isolated ferroelectric capacitance is unstable in nature. If you try to put charge here, it will fall to one of the minima. And that is why in the impedance analyzer, when you are judging, it is showing the value of capacitance as positive. Rather than showing it as negative, it is showing positive. If you try to put a charge here, it will fall to one of the minimas. And that's why this particular region tells about the negative capacitance. Because if you go for a dielectric capacitance and you plot a U versus Q, it will be upward parabola. And here this is a inverted parabola. So this signifies the presence of negative capacitance. But if you try to put one of the charge here, so it will fall to one of the minima. It's like a transient state, so it vanishes. That's why you are not able to see any negative capacitance in the impedance analyzer. It's showing a positive capacitance. So as you can see, first we'll go through this ferroelectric capacitor. So this is the charge versus voltage characteristic for this. Now, first of all, before going for negative capacitance, what is positive capacitance? Let's see what is positive capacitance. So like in resistance, if you are increasing the voltage, current is increasing, that is positive resistance. And negative resistance is what? If you increase the voltage and current is decreasing, that is negative capacitance. Similarly, in capacitance, there is an expression Q equals to CV. If you increase the voltage, charge increases, means positive capacitance. And if you increase the voltage, charge decreases, then that becomes your negative capacitance. Now let's see this. So this is the characteristic which I have obtained through this expression. Vf equals to alpha QF plus beta QF cube. This is a mathematical expression for a ferroelectric material. And this particular equation is known as LK equation, Landau-Khalatnikov equation. It was given by a scientist. Now, this alpha and beta, just now in the previous slides I had told that alpha and beta was dependent upon the value of corrosive field and remnant polarization. So using that, I'll calculate the value of alpha, I'll calculate the value of beta, and I'll put this in equation. Obviously for different values of TFE, like 30 nanometer, 60 nanometer, 90 nanometer, 120 nanometer. For different values of TFE, I'll get different values of alpha and beta. So I have extracted the value of alpha, I have extracted the value of beta for all the four combinations: 30 nanometer, 60 nanometer, 90 nanometer, and 120 nanometer. And I have plotted this characteristic, charge versus voltage. Now you can see here in this particular region, as we are increasing the voltage, the charge I am increasing the voltage, the charge is decreasing. So that confirms the presence of negative capacitance. Similarly, energy landscape for ferroelectric can be obtained by following equation: U equals to alpha by 2 QF square plus beta by 4 QF to the power of 4. Similarly, alpha beta value I already know.
Sir, and which
increase हो रहा है ना?
No, ये like if I try to plot, it will be something like this now.
Initially it is increasing.
Slope. I'm
Increasing
talking
yeah.
about slope. Slope is what?
अच्छा gradient.
Gradient is falling.
Okay, graph is
So
Gradient.
if charge versus voltage, it will be something like this. Then the gradient is positive.
Yes.
If it is like this, it's negative. So this signifies the presence of negative capacity. Now UQ, U versus Q. Energy of a dielectric normal capacitor is upward parabola. Now here, if we see U versus Q for ferroelectric capacitor in this region, you see a inverted parabola over here.
Yes.
So that confirms the presence of negative capacitance. But the isolated negative ferroelectric or a negative capacitance state is highly unstable in nature. So this is the charge versus voltage, and this is the energy versus charge for a isolated ferroelectric capacitor. Now the basic doubt,
This energy is decreasing.
Yeah.
In second graph.
yeah, it's like in terms of radius of curvature or the parabola, we can say that here the capacitance is negative.
Negative.
Now the common doubt, like as I have solved these equations as a part of equation, this equation, I am able to see that negative capacitance exists, because in the first graph the gradient is negative and here the radius of curvature is negative. But when you do the experiment, like I told, there was an experiment which was conducted in UC Berkeley, and they kept that ferroelectric capacitor in impedance analyzer, and they obtained the value as positive, and I told you the reason also. So the common doubt what everyone has, how you can confirm the presence of negative capacitors. Answer to this question is, you can confirm if you add a dielectric capacitor in series to ferroelectric capacitor. Now next is my heterostructure only. Next is heterostructure. So what I have done, I have added a dielectric capacitor.
It will not follow the simple network law.
That is what. I'm coming on to it. So what happens in normal KVL, what we say, if two components are there, I have applied a source Vs and there is a drop across two components V1 and V2. So we will say Vs equals to V1 plus V2 as per our conventional Kirchhoff's voltage law. But violation of that law is actually telling us the presence of negative capacitance. I'll come on to that in a few moments. So now this is my FED heterostructure. Now, as I told that impedance analyzer was not able to tell me about the negative capacitance. So I have added a dielectric capacitance in series to it. Normally if two capacitance are in series and I apply a certain voltage, Vs, So equivalent capacitance will be what? It will be reduced. But if somehow I am getting the more capacitance, that confirms the presence of negative capacitance. If two capacitance are in series, equivalent will be obviously less than both. But if I am getting, if suppose I am getting higher value, that confirms the presence of negative capacitance. Similarly about voltage drop. If two components are there and I'm applying a certain voltage, the voltage drop across one of the component will always be less than the supply. Common sense. But if somehow I am getting voltage drop across one of the component higher than the supply, then that tells me about presence of negative capacitance. That is not possible in a normal passive component element. Suppose I am having two capacitors which are both are positive. So in that it's not possible to get amplification. The amplification which I was talking previously. So let's see. So here what I have done, I have FED heterostructure. I have added dielectric capacitance in series. Now let's see how this charge versus voltage changes. So the expression for this will be Vs equals to alpha plus 1 by CD QF plus beta into QF cube. Now when I solve this equation, I'll get this characteristic QF versus voltage. Here TFE equals to 0 signifies that I am having a dielectric capacitance, because the structure is something like this. I'll just go back. This is the structure. So here if I put TFE equals to 0, that means I am having a dielectric capacitor. And if TFE is having some value, so it's a combination of ferroelectric and dielectric. So it is heterostructure. So this I have plotted the charge versus voltage and energy versus charge. Now, here you see this is for the dielectric capacitor. TFE equals to 0. This dotted line tells me about the dielectric capacitor. And the other four lines, blue, red, green and brown, they corresponds to 30 nanometer, 60 nanometer, 90 nanometer and 120 nanometer. So that is for the heterostructure. Now, what can we get the inference from this characteristic and this characteristic? So what it tells, that my capacitance has increased, total capacitance has increased. So we'll come to that in the next slide also, but using this also we can say that total capacitance has increased, because the UQ curve is more flatter. Flatter curve means the capacitance has increased, because if you U equals to D2Q by DC square, I think.
U equal to dq by dt square.
No, because U equals to Q square by 2C. So if I try to put in terms of capacitance, this will tell me more flatter. So this, if you see this brown curve is more flatter. So flatter curve means the capacitance has increased. This will be more clear in the next slide when I'll be telling about directly capacitance versus voltage. Now this is something which I was talking about. Now if you see the capacitance, this is TF equals to 0, the capacitance is here, and for all the other cases, the capacitance is increased, which is not possible when I am having normal two capacitances.
Brown line is?
Brown line corresponds to 120 nanometer.
120 nanometer.
TFE, this green line corresponds to 90 nanometer, red line corresponds to 60 nanometer, and blue line corresponds to 30 nanometer. And this dotted line corresponds to 0 nanometer. So now what has happened? This is what I was talking about, how to confirm the presence of negative capacitance.
So TFE 0 means when we are having only dielectric.
Only dielectric.
Then
Only
we
dielectric.
observe the capacitance. That time FE material is not.
No, not there. Only dielectric.
Individual dielectric.
Only dielectric is there. Now if you can see,
Only
Only dielectric, only dielectric.
No any other material is there.
No other material is there.
So capacitance is constant then?
Constant only, this dotted line.
It is not increasing.
No,
Only dielectric.
only dielectric is there.
Only dielectric.
Only dielectric is there. And for these cases, there is a hot heterostructure.
All these are heterostructures.
No, no, no.
Remaining.
Remaining are
First
heterostructures.
TFE0 means
This is-
conventional case, conventional case.
This is just a case of dielectric.
Uh,
And TFE equals to 30 nanometer means dielectric is there
Plus.
plus
FE.
ferroelectric is also there. And the ferroelectric thickness is
okay, okay.
30 nanometers.
Most flat curve we are getting.
Huh.
FE
So,
is highest. More capacity.
At TFE equals to 120 nanometer, there is a sudden jump in capacitance, which is not possible in case of normal two capacitances. So this confirms the presence of negative capacitance, which is not possible in any two random capacitances. Similarly, if we see the voltage drop, this is the voltage drop, this is the supply voltage, and this is the voltage drop. Now, this dotted line again is for TFE equals to 0, and the other lines are for TFE equals to 30 nanometer, 60 nanometer, 90 nanometer, and 120 nanometer correspondingly. Now, if we see, there is a voltage amplification over here.
Yes.
There is a voltage amplification, but normally it doesn't happen in a normal capacitor, because if there are two capacitance, suppose I say the voltage drop across ferroelectric is Vf and dielectric is Vd and supply is Vs, then what can I say? Vs equals to Vf plus Vd. So Vd has to be less than Vs.
Yes.
But here what is happening?
It is increasing.
Vd is more than the supply. Vd is more than the supply. So this again tells me that something is happening and there is a negative capacitance over here. So in the next talk, in the talk number 2, which I will be giving tomorrow, there is a big table which I have made, so it will be more clear. So this is,
It is all about the thickness of dielectric.
Ha,
So
but,
it can further increase the
no,
thickness of
there is a catch over here. So you cannot randomly increase the ferroelectric thickness.
So,
What is the hyperparameter?
sir, it is basically a characteristic, but why it happened? Because logic behind it.
Logic behind is the internal of ferroelectrics. Internal of ferroelectrics. You have to go deep into ferroelectrics, because if you talk about this alpha, which is the an anisotropic constant, it's actually 1 upon 2 epsilon, and the permittivity here is negative. Negative for this material for a limited range.
For only a limited range.
Limited range means for certain values of Vs, like here, you see, this is falling only up to this point, in this range only. Rest, here only the gradient is negative.
Means we are using different dielectric, then the characteristic will change.
Different dielectric means
Having different dielectric strength.
thickness you are talking about, sir. Thickness it will change. That is what I am saying. As sir was pointing out, if we keep on increasing the
characteristics.
ferroelectric thickness, are we able to get amplification? No, that is not the case actually.
At what limit we have?
There is a limit which is known as critical thickness. So beyond that critical thickness, we cannot exceed the ferroelectric thickness. Why? Because suppose I want to use this particular thing in a digital application, and if in device hysteresis comes, hysteresis is good for memory kind of application, but if I want to use my device in a digital application, this hysteresis is not good. So if you keep on increasing the ferroelectric thickness beyond a critical limit, there will be a hysteresis in my characteristic. So I cannot arbitrarily increase the value of ferroelectric thickness. It has some limits, and that limit I will be discussing more in the talk number 2. I made a one table in which how to in this case the critical thickness is 120. That's why I have not exceeded beyond 120 nanometer. So
Sir, TFE 0 millimeter means ferro material is not there.
not there. Only dielectric is there.
Then what is the thickness of dielectric?
Dielectric I have taken as 1 nanometer. 1
But
nanometer.
it's not presented in this slide anywhere.
No, it is there. One second. This is the structure. Correct. Now, let's say the ferroelectric is having thickness TFE and dielectric is having thickness TDE.
TD something.
Okay. Now, TFE equals to 0. Means only dielectric is there.
Yes.
Quite obvious. And if TFE is there, then it becomes a heterostructure.
Yes.
Means when we are TFE is there, then also we are including the dielectric thickness.
No, dielectric is fixed.
Thickness
I'm not altering dielectric. I'm altering only ferroelectric. So ferroelectric is increased from 0 to 120. In first case it is 0. When it's 0, it corresponds to dielectric capacitor.
But means main role is.
No, he is asking, is there any change if we are changing the value, the thickness of dielectric?
It will change. It will change. It will change. It will change.
It will change.
Because everything is dependent upon matching of ferroelectric and dielectric.
What actually the internal phenomena behind it?
Ferroelectric.
That is what I'm telling. Because the permittivity becomes negative.
Okay.
Because this alpha, if you see, just see, alpha equals to minus.
Minus. Okay.
Alpha equals to minus. So it is saying that permittivity is negative. Minus 3 root 3 by 2 VC by Q naught.
नहीं मतलब ठीक है ये these are basically constant.
Yes.
ठीक है they are coefficient basically.
Yeah, coefficients only.
Actual क्यों है मतलब coefficient they are calculated on the basis of experiment.
Correct.
Actually में क्यों ऐसा ये value क्यों आ रही है इस तरह की?
Which
Why
value?
this formula is derived in this particular for this particular value?
No, this
The value of alpha is calculated on the basis of some experiment.
is correct.
तो वो internally कैसे उसमें हो रहा है material में?
मटेरियल में वही ये तो मैं बता रहा हूँ ना कि अल्फा क्योंकि नेगेटिव हो रहा है यहाँ पे हमारा.
ये तो आपने कोई कांस्टेंट है या कोएफिशिएंट का है ऑन द बेसिस ऑफ एक्सपेरिमेंट आपने कैलकुलेट किया हुआ है उससे आप एक्सप्लेन कर रहे हैं स्ट्रक्चर में ऐसा क्यों हो रहा है?
So you are saying physically what is happening. Physically what is happening. So it's like how should I tell? Okay. Yeah, understood. I understood. You are trying to understand what happens inside the. So, like in normal dielectrics, what happens? The polarization direction is, I think, in same as direction of field.
Yes.
But
we applied a field.
When we apply a field, but here what happens? The direction of polarization is opposite to the applied field.
So is there any internal development of field?
Internal field also be there. No?
Otherwise कैसे?
Local field and the total field.
कोई molecular structure होगा इसका कुछ?
Yes. This is a perovskite material AbO3. So it has A equals to B and C is like 3 constants A, B, C are there. So A is equals to B and C is a bit lesser as compared to A and B, and this is the non-centrosymmetric molecule. So it's not at between. It is displaced actually.
Displaced from the center.
Center. Then which is giving, that is why this kind of material is behaving like this. Because I am not much into material, I am more into application part of it.
Our objective is to replace MOSFET with this.
No, not MOSFET actually, sir. MOSFET, no.
This replacement of.
नहीं, actually I think the main objective is voltage amplification from passive devices.
Yes. So what will happen next talk? What will happen? We in MOSFET we are having a substrate. Substrate N plus source drain is there. Above to it we are having a dielectric SiO2 which we are oxidizing and getting, and above to it that we are having a gate, and on gate we are applying certain voltage. Now above like that gate we'll try to put this ferroelectric. We'll try to put this ferroelectric, or I can say we'll try to put this ferroelectric over to dielectric. So what will happen? There will be a voltage amplification over there.
Yes.
And when voltage amplification is there, I'll require less voltage to turn on my device.
Yes.
And there will be a low power dissipation. Energy will be saved.
Okay.
And subthreshold swing will be altered.
It will
Reduce. Yeah. So that will be in the next talk actually. So I hope this was.
Now we come to the objective.
Now we have understood what is happening. Now we'll in today's lab session also I'll tell this only. It means how to plot this, how I've got this, how I got the value of alpha, how I got the value of beta, and we'll put it inside an equation and we'll see how these characteristics have come. So let me conclude. So negative capacitance in ferroelectric is unstable at every thickness.
Yes.
So for stabilizing it, we need to put a small positive capacitance in series to it. So when we put a small positive dielectric capacitance, your negative capacitance state stabilizes, and you are able to visualize the negative capacitance by some virtual phenomena, not directly, but virtual phenomena, because your capacitance is increasing, as well as there is a higher voltage drop across the dielectric. So this is what is written over here. The unstable nature can be stabilized by adding a dielectric in series to ferroelectric capacitor, and the voltage amplification is achieved across the dielectric and is greater than the supply. And passive voltage amplification can also be studied. So this is a few references which I have taken from.
So your papers on this topic?
Yeah, I have papers on this topic, but I think here I have not included. This is the results from one of my paper only. So this was published in IET MNN, micro nanoliters letters. So these are the results from one of my article only.
ये old topic है या नया है?
नहीं, ferroelectric was
ये negative capacitance.
negative capacitance
ये तो काफी older.
using in MOSFET was started in 2008. Although the discovery of ferroelectrics was taken long back in 90s, I think. But in 2008, one guy from, I think, Purdue University, Saif Salahuddin, he was working under Professor Supriyo Datta. He came up with an article on this negative use of negative capacitance in MOSFET to alter the body factor and somehow get the subthreshold swing below 60 millivolt per decade. So at present only many researchers are working on this particular topic.
काफी काम हो गया होगा.
First article particularly related to this came on 2008.
जो publications होंगे वो तो different thickness के लिए लोगों ने किए होंगे या कुछ और किया है?
बहुत सी चीजें हैं सर. Like
What is the role of two metal and what is the role of two metal in this all this?
contact तो देना पड़ेगा ना. Contact somehow, like in normal dielectric also you have a contact. So contact has to be there.
piezoelectric material use कर रहे हैं तो
Piezo नहीं sir, this is ferro. Piezo is something.
फेरोइलेक्ट्रिक मटेरियल यूज कर रहे हैं तो जो कांटेक्ट पॉइंट्स है उससे मैचिंग भी करवानी पड़ेगी जो आपका, क्योंकि मोबिलिटी अलग अलग हो सकती है ना चार्जेस की.
Between dielectric and ferroelectric. Because here we have taken an ideal scenario. Here I have not taken any interface effect between ferroelectric and dielectric.
There may be some
हाँ,
interface effect.
So that you are talking about, I think, single mode and multi-mode, all those things will come into picture. But this is a normal analysis where I have taken an interface as ideal. Interface here is ideal.
So we have to analyze the overall device characteristic.
Yes, yes, yes.
But we don't have any physically negative capacitor.
Physically, in the sense, sir, means in the market you won't get any negative capacitance. You cannot go and buy an.
Can we
But
make the
you can make. You can make.
ever developed any kind of negative capacitor?
Yes. Many experiments in foreign universities and even in, I think, India also, few guys have developed this heterostructure and shown. Like this is everything mathematical. Everything I've done in mathematical. So they have fabricated and seen the signatures of negative capacitance. It's not like only in mathematics I'm getting. They have done it experimentally and it's a well-known phenomenon. So I hope that I was able to convince.
We understand new thing. Also we got the concept that if you add one positive positive dielectric, then only we can get the negative
So there is a table also, if I was able to better. There was one table also. I think that I have kept for top number 2. Can I minimize? Now we can get a much more clear idea with this table. I have taken 2 capacitances, C1 and C2. So C1 is a fixed capacitance, means you can consider it as dielectric capacitance. And C2 is a variable capacitance. It is because we are varying thickness, capacitance is a function of thickness. So C2 is a variable capacitance which I am varying from 4 to -7. So now equivalent will be C1 C2 upon C1 plus C2.
Yes.
So for first case it is 2. Next 1.7, 1.33, 0.8 and 0 here. So what is happening here? C equivalent is smaller than C1. Now when it is negative, so slowly I am going to negative. Here it was positive, from 4 to 0 it was positive, now I am going to negative. -1, the value is -1.33. -2, the value is -4. -3, the value is -12. Now you can see C equivalent is negative. Now let's come here, 4 minus 4. So it's like undefined. Now I further go below, -5, -6 and -7. Now you see, C equivalent is larger than C1. And this amplification only I was talking about in my
For a limited range.
for a limited. So here the thing which you were saying that can we increase the thickness further, from here only that critical thickness will come. So if you see, when this capacitance C2 is a negative capacitance and C1 is a positive capacitance. C1 is a fixed capacitance, C2 is a variable capacitance. When this is close to this is 4, this is -1. I got the maximum value of C equivalent.
We use C1 for a stable capacitance.
C1 is a stable capacitance. So it's like if I put 4 here instead of 5, it should be like, if it is -4.5, then I will get even more value of C equivalent. So the condition here is,
We can use it from -1 to -3 only.
better we can use, but it should be, because if we are trying to get C equivalent is larger than C1, so from here we can get to one conclusion that mod of C2 should be greater than C1. So when mod of C2 is greater than C1, then only I will be getting amplification. So from this, that critical thickness comes into picture, because I have to make mod of C2 greater than C1. And thickness, the capacitance is a function of thickness. So this is one thing. I'll discuss deep onto it in the next session
But
also.
this is not tabulated as per this formula, sir. This is table.
This is a general table where I have taken C1, C2, some random numbers, and just try to make the audience understand what is happening.
Experiment.
Now this is not experiment, this is just a random data.
Random data.
Random data. This is just a random data through which I am trying to
So the
Yeah, explore the-
explain a bit easy in a easier fashion.
so the essence of.
So what is happening actually? So here you can see now, like if mod C2 is greater than C1, I get C equivalent larger. Before here I was not getting any capacitance enhancement. In this condition only, capacitance enhancement is there. So I think this is, if anything is there, feel free to ask. So this is like a very, you can simulate these kind of things even in MATLAB also. This can be done in MATLAB also. This is very simple analysis. So in the afternoon session, I think I have one lab session. So in that I'll tell about an online tool which is known as Desmos. It's like MATLAB only, where you can put an equation and get a graph. So all these graphs will be, which I showed in the PPT number 1, we'll be doing in the lab session also. If any doubts are there, feel free to ask me. I'll try to answer those doubts.
That mathematical model is difficult, sir. Rest other things. Mathematical modelings, the formulas, whatever we are getting, that is very sometimes difficult. Rest other things are okay.
No, the only thing which you have to take is these equations exist from long back, 1920s and all these ferroelectrics. But the critical thing here is to get the values of alpha and beta. Because alpha and beta, how we'll get alpha and beta will get through remanent polarization and corrosive field. For every material that varies. So that you have to refer to some good articles, you have to get those values. Then you have to extract the value of alpha and beta, and then you can do this type of analysis. And the main thing is this is just FEDE heterostructure. The next thing is how you can utilize this FEDE heterostructure in a MOSFET to improve its performance. Because lastly what we have to do, we have to do some computing using MOSFET. So we are utilizing this ferroelectric to enhance the properties of our MOSFET.
So I think this is the end of the first session. So now I would like to give thanks to Dr. Awadhiya for his first session. Very knowledgeable session. Thank you, sir.